Hello, and welcome to another SolidCAM Professor introductory video. My name's John, and here I want to show you just how easy it is to program with iMachining, use the technology wizard, simulate toolpath, and finally, generate G-code. Now, before I get started, I should note that this video is only meant for viewing and is just an introduction to programming with iMachining. Just keep in mind that it's not one of our tutorial videos intended to help you practice using the software. I might explain a few key points, but that's about it. So now I'll get started with my quick introduction to iMachining. Let's have a look at my screen. Now again, as you can see, I'm working in SolidWorks. The nice thing about SolidCAM is that I can perform all my CAD and CAM without ever having to leave the SolidWorks environment. SolidCAM provides a seamless single window integration to SolidWorks, and the created CAM part maintains full associativity to the SolidWorks design model. Now, here I have my model on the screen. You'll notice that I actually have two models, one representing my stock material and the other representing my target shape. As I've done here, the best thing to do really is to model your stock ahead of time. You don't have to, but it is recommended. Now, I want to use SolidCAM's revolutionary iMachining technology to define the rough and finish machining of this part, taking it from the stock to the target shape. Since I'm ready to machine, I'm ready to start SolidCAM and create the CAM part. In the SolidWorks main menu, I'll click SolidCAM, New, Milling. The New Milling Part dialog box is displayed. Since this video is only for demonstration purposes, I customized my CAM settings to do a few things for me. First, my CAM project will be created using the internal mode by default. This mode will store the SolidCAM data inside my SolidWorks part file. Since I'm the one who built the CAD model and am now performing the CAM programming, it makes sense for me to work using this internal mode. Now, the CAM part name automatically defaults to the SolidWorks part name plus a milling designation, since this is a milling project. And since I built the SolidWorks part using millimeters, the units of measurement automatically default to metric in SolidCAM. I'll click OK to create the CAM part. After it's created, you'll notice some actions being performed in the background. That's actually SolidCAM automatically defining the CAM part per my requested CAM settings specifications. After the automated CAM part definition process is completed, SolidCAM prompts me to let me know that I can start adding my operations. I'll click OK, and now I can start using iMachining. To do so, I'll go to the SolidCAM Manager on the left to add my first operation. I'll right-click Operations, Add Milling Operation, and select 2D iMachining. When the first iMachining operation is added to the CAM part, I have to define the machine and work material parameters. These selections populate to the CAM part definition and affect the entire CAM project. The selections that I make now will affect the cutting conditions that are output by the technology wizard for each iMachining operation. I'll first define the machine by selecting Haas SS from the list. This particular machine file is included with the installation of SolidCAM. I'll then click the Next button to define the material. There are also more than 70 materials supplied with the system. For the purpose of this introductory video, I'll just choose a type of aluminum from the list. Now, when I click Finish, the iMachining operation dialog box is displayed, and the technology type automatically defaults to iRough. Following the SolidCAM workflow in the tree here on the left, the first thing I need to do is define the machining geometry. So on the geometry page, I'll click the New button. Now, it's important to note that the geometry in iMachining is defined as a pocket that can be closed, open, or semi-open. You'll see that this part is a perfect example showing all these types of geometries. So for the first operation, I want to define the rough machining of the outside contour. And to do that, I have to define the geometry as an open pocket with island. The first chain I need to select is the outer chain. In the SolidWorks graphics area, I'll pick on the top edge of my stock model. I'll close the chain by using Auto Constant Z, and then I'll accept the chain selection by clicking Yes. Next, I'll pick the chain that runs along the outside contour of the target model. Again, I'll use Auto Constant Z to close the chain, and I'll click Yes to accept the chain selection. Now in the chain list, I want to right-click Chain 1 and choose Mark Chain as Open. This will inform the iMachining technology to approach from this outer chain. I'll click OK to confirm the geometry selection. Next, I have to define my tool for the operation. In fact, I'll define just one tool and I'll use it in all my upcoming iMachining operations. So to start the tool definition, I'll move down to the tool page and click the Select button. I'll click the Add Milling Tool button and choose End Mill from the Milling Tools list. Under the Topology tab, I'll set my tool parameters as follows. I want to use a 9mm diameter tool. I'll keep the default length parameters, which gives me a cutting length of 24mm. Finally, the tool I'm going to use actually has 4 flutes. Under the iData tab, I'll use the default 45 medium value for the helical angle parameter. This parameter, along with the tool's diameter, cutting length, and number of flutes, affects the cutting conditions and step-down values that are generated by the technology wizard. To confirm the tool definition and choose the tool for the operation, I'll click the Select button. Now, believe it or not, the last of the parameters that I have to define are the milling levels. So I'll move down to the Levels page to define on what Z levels to start and end the machining. These Z levels can be picked directly on the model. First, I'll define the upper level, which is the top face of my stock model. Then I'll define the pocket depth, which is the bottom edge of my target model. I'm also going to define a delta depth to perform machining deeper than the part bottom edge. I'll set the value to -0.76 millimeters. Now let's switch to the Technology Wizard page for just a moment. With only the geometry, tool, and levels defined, the iMachining technology produces on-the-fly cutting conditions, as you can see in the step-down and output cutting data sections. Using the machining level slider, you can of course select from 8 different levels of aggressiveness. This wizard enables you to choose from calculated sets of cutting conditions that are optimal for your particular machining case. For this example, I'm just going to use the default level of 3. On the Technology page, note that my wall island offset parameter is set to 0.24 millimeters by default. Now that I'm finished with the operation definition, I'll simply click the Save and Calculate button to add the iMachining operation to the CAM tree and calculate the tool path. Now for this particular video, I'll simulate the roughing and finishing toolpaths at once using the Host CAD mode. Next, I want to define the finished machining of the outside contour. And to do that, I can simply click the Save and Copy button, and then just change the technology type to iFinish. My geometry, tool, and levels definitions are all copied over from the previous iRough operation. The same Technology Wizard settings will also be used. On the Technology page, the wall island offset defaults to 0. I also want to mention that on the iRest Data tab, the iMachining technology automatically inputs the data needed for calculating rest material. The finished machining is now defined, and I can click Save and Calculate to add this iFinish operation to the CAM tree and calculate the toolpath. Now, I'll click Simulate to open the Simulation Control Panel. I'll select both the iRough and iFinish operations in the SolidCAM Manager to make sure that both operations run during simulation. Using the Operation Step Mode button, I'll first show the roughing toolpath, and then I'll show the finishing toolpath. Both look good, so I'll exit the simulation and the iMachining operation dialog boxes. Next up, I want to define the machining of the center pocket. I'll again go to the SolidCAM Manager, where I'll right-click Operations, Add Milling Operation, and select 2D iMachining. The iMachining operation dialog box appears, and iRough is used for the technology type by default. I'll click the New button on the Geometry page to define the machining geometry. For this operation, the geometry is defined as a closed pocket. In the SOLIDWORKS graphics area, I'll pick on the lower contour of the pocket. I'll then select Auto Constant Z to close the chain, followed by clicking Yes to accept the chain selection. Finally, I'll click OK to confirm the geometry definition. Next, I'll move down to the Tool page and click the Select button. I'll choose the already created 9mm end mill by selecting it from the Part Tool table. I'll then click Select to confirm the tool definition. Now I can move down to the Levels page to pick the milling levels. And I'll start with defining the upper level, which is again the top face of my stock model. Then I'll define the pocket depth, which is the bottom face of the center pocket. I'll use the default cutting conditions generated by the Technology Wizard, and again, a 0.24mm allowance will be left on the walls as shown on the Technology page. Moving down to the link page, I can see how the iMachining technology will enter this closed pocket. A helical entry will be performed at a ramping angle of 4 degrees. This value actually coincides with my chosen default machining level of 3. I'll click Save and Calculate to add this iMachining operation to the CAM tree and calculate the toolpath. To define the finished machining of the center pocket, I'll click the Save and Copy button, and then I'll simply choose iFinish for the technology type. The copy geometry, tool, and levels definitions are all used along with the same cutting conditions that were generated by the wizard. Again, the wall island offset defaults to 0, and the iRest data is automatically defined. By clicking Save and Calculate, I'll add this iFinish operation to the CAM tree and calculate the finishing toolpath. Finally, I'll open the Simulation Control Panel with the Simulate button. I'll select the operations that were defined to machine the center pocket in the SolidCAM Manager. Then, I'll click the Operation Step Mode button. You'll see that the helical entry is performed, followed by the pocket roughing toolpath. I'll click the Operation Step Mode button once more to see that the finishing is performed in the corners first, followed by a final pass along the walls. And these results look good, so I'll exit the simulation and the iMachining operation dialog boxes. Next up, I want to define the machining of the pocket ledge. I'll once again go to the SolidCAM Manager, where I'll right-click Operations, Add Milling Operation, and select 2D iMachining. When the iMachining operation dialog box appears, I'll click the New button to start the geometry definition. For this particular operation, the geometry is defined as a semi-open pocket. In the SolidWorks graphics area, I'll first pick on the lower contour of the pocket ledge, and using Auto Constant Z, I'll close the chain, and then I'll click Yes to accept the chain selection. Next, I want to right-click Chain 1 in the chain list and then choose Mark Open Edges. When the Mark Open Edges dialog box appears, I'll simply have to pick on the outside edge of the pocket ledge. This will inform iMachining to use that edge for entry. I'll click OK to accept the edge as open, and then I'll click OK again to confirm the geometry selection. Moving down to the Tool page, I'll choose my tool for the operation just as I've done previously. To finish up the operation definition, I'll switch to the Levels page to pick the milling levels. I'll define the upper level first, which is again the top face of my stock model. Then I'll define the pocket depth, which is the bottom face of the pocket ledge. On the Technology Wizard page, I can see the generated cutting conditions based on the default machining level aggressiveness of 3. And again on the Technology page, I can see that a 0.24mm allowance will be left on the walls. I'll click Save and Calculate to add this iMachining operation to the CAM tree and calculate the toolpath. Finally, I'd like to define the finished machining of the pocket ledge, and to do that, I'll again click the Save and Copy button. I'll choose iFinish for the technology type. All my definitions are copied over from the iRough operation, and the iMachining technology inputs the data needed for finishing. I can click Save and Calculate to add this iFinish operation to the CAM tree and calculate the toolpath. Now, I want to see how the wireframe toolpath performs for machining the pocket ledge. I'll click Simulate, and then select both operations to start the simulation. Using the Operation Step Mode button, I want to see the tool approach from the outside and then remove the material from the ledge. Looks good. I'll click the Operation Step Mode button once more to watch the finishing toolpath. The toolpath is showing me exactly what I want to see. Now I'd like to generate G-code so I can start cutting with iMachining. But first, I want to perform a machining simulation on the solid model to run a final verification on the generated toolpath. And I can do that by using either the Solid Verify mode or by just enabling the Solid Verification option in HostCAD. For this example, I'll just run the Solid Verification on the SolidWorks model. I'll click the operations header in the SolidCAM Manager to start the simulation at the beginning. By clicking play, I can watch the simulation run in its entirety and see that the iMachining toolpath looks great. Now I know I'm ready to safely cut this part on my machine, but first, I need to generate a G-code file. So I'll exit the simulation and the iMachining operation dialog boxes. Then I'll go to the SolidCAM Manager and right-click Operations, G-code All, Generate. The generated G-code opens in Notepad, and I'm now ready to machine this part on my 3-axis Haas SS. So there you have it. As you can see, it's quite easy to cam a part with iMachining, and even easier still to generate G-code with SolidCAM. For more great SolidCAM Professor videos, visit the Professor page at www.solidcam.com.